Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Filters 2 under the paper Measurements and Instrumentation. So students, let us see what we are going to learn in this module. In this module, higher order filters such as third order and fourth order are discussed. The types of bandpass filters, that is, wide bandpass and narrow bandpass filters, are studied. The expression for gain for narrow bandpass filter is derived and the frequency response is obtained. Band reject filters are studied as wide band reject and notch filter, and the frequency response is discussed in detail. Finally, an all-pass filter is studied. Let us begin with the higher order filters. We have already studied in the previous module status filters 1 that in a first order filter, the gain of filter changes at a rate of 20 dB per decade, whereas in a second order filter, the gain changes at a rate of 40 decibel per decade. Thus, as the order of filter increases, the filter approaches to its ideal behavior. That is, change in gain in the stop band of filter becomes more steep near the cutoff frequency. Higher order filter of any order, that is, third, fourth, and so on, can be made using the first order and second order filters. For example, a third order low pass filter can be made by integrating a first order and second order low pass filter together in series. Fourth order filter. A fourth order filter can be made by cascading two second order low pass filters and so on. In this way, filters of various orders can be made. However, it is important to understand that as the order of filter increases, its size also increases. Also, with an increase in the order of filter, the observed stop band response deviates increasingly from the theoretical stop band response. Thus, accuracy of the filter declines by increasing the order of filter. Let us study the gain of the higher order filters. The overall gain of the higher order filter is equal to the product of gains of the individual stages, since the values of frequency determining resistors and capacitors, that is R and C, are kept to be same everywhere in third and fourth order filters shown in the figure. Therefore, the high cutoff frequency is same for the third and fourth order filters. The cutoff frequency fH is given by fH is equal to 1 divided by 2 pi RC. The frequency response of third and fourth order low pass filters is shown in the figure. Similar to the first and second order high pass filter, third and fourth order high pass filters can be made from third and fourth order low pass filters by simply interchanging the positions of frequency determining resistors and capacitors in the constituting individual low pass filters. Although the stop band response of the higher order filter is closer to ideal case, but higher order filters are more complex, occupy more space, and are more expensive. Let us now come on to bandpass filters. A bandpass filter allows only a particular band of frequencies to pass through it without attenuation and blocks others. The band of frequencies is determined by certain parameters such as lower and higher cutoff frequencies, which are FL and FH, center frequency FC, bandwidth of the filter represented as BW, pass band gain, and quality factor Q. If the lower and higher cutoff frequencies are FL and FH, then bandwidth of the bandpass filter will be given by BW equals FH minus FL. Bandpass filters are basically classified into two categories as wide bandpass and second narrow bandpass. It is difficult to define that whether a particular filter is wide bandpass or narrow. However, in order to differentiate the two, a parameter called figure of merit or quality factor Q is introduced. Q is a measure of selectivity of the filter. That is, higher the value of Q, more selective is the filter, or narrower is its band. Q is related to the center frequency of the filter and bandwidth by the equation Q equals Fc by Bw, which equals Fc divided by Fh minus Fl. A filter is said to be a wide bandpass filter if its quality factor Q is less than 10, whereas if Q is greater than 10, the filter is said to be a narrow bandpass filter. For a wide bandpass filter, the center frequency Fc can be defined as Fc equals square root of Fh into Fl. In a narrow bandpass filter, the output voltage peaks at the center frequency Fc. Let us take up wide bandpass filter. The circuit of a wide bandpass filter is formed by cascading a high pass and a low pass filter. The order of the wide bandpass filter depends on the order of its constituting low pass and high pass filters. That is, to obtain a first order bandpass filter where the gain rolls off at a rate of plus minus 20 dB per decade, first order high pass and low pass filters are cascaded. For a second order bandpass filter where the gain rolls off at plus minus 40 dB per decade, second order high pass filter is connected in series with second order low pass filter. The circuit diagram of first order bandpass filter is shown in the figure. Voltage gain of the bandpass filter is equal to V0 by Vn. In terms of the output of the first order high pass filter, which is V0 prime, the ratio of output to input voltage can be expressed as V0 by Vn is equal to V0 divided by V0 prime into V0 prime divided by Vn. That is, voltage gain of the bandpass filter is equal to the product of gain of high pass and low pass sections. Therefore, using equations 3 and 6, we have for the gain of low pass and high pass filter as discussed in the previous module, V0 by Vn is equal to AFL into within the brackets J into F by FL divided by 1 plus J into F by FL brackets close into AFH divided by 1 plus J into F by FH. This equals AFL into AFH into within the brackets J times F by FL divided by 1 plus J into F by FL into within the brackets 1 plus J into F by FH. This equals AFL into AFH into within the brackets J into F by FL divided by 1 minus F square divided by FL FH plus J into within the brackets F by FH into F by FL brackets close and overall brackets close, where AFL is equal to 1 plus RF prime by R1 prime is the voltage gain of the low pass filter. AFH is equal to 1 plus RF by R1 equals voltage gain of the high pass filter. FH is equal to 1 by 2 pi R prime C prime is the high cutoff frequency of the filter. FL is equal to 1 by 2 pi RC is the low cutoff frequency of the filter. the magnitude of voltage gain, that is modulus of V0 divided by Vn, is equal to AFL into AFH into F by FL divided by square root of 1 plus F by FL whole square into 1 plus F by FH whole square. So the magnitude can be simplified to be equal to AFT into F by FL divided by square root of 1 plus F by FL whole square into 1 plus F by FH whole square, where AFT is equal to AFL into AFH is the total passband gain of the bandpass filter. Therefore, the total passband gain of the bandpass filter is equal to the product of individual passband gains of low-pass and high-pass filters. The frequency response of the bandpass filter is shown in the figure. From the expression of magnitude of voltage gain, it can be inferred that for frequencies in the first case, that is frequencies f much less than fl and fh, terms f by fl whole square and f by fh whole square in the denominator will be very small, and thus can be ignored in comparison to 1. Therefore, the expression for magnitude of voltage gain modulus V0 by Vn equals AFT into F by FL. Thus, gain of a wide bandpass filter is directly proportional to frequency at low frequencies. As frequency increases, gain increases. We discuss the second case where the frequencies F lies between FL and FH. Now the term F by FL whole square in the denominator will be very large in comparison to 1. So the expression of gain of a wide bandpass filter turns out to be the same as that of a low pass filter. That is, modulus V0 by Vn equals AFT into 1 divided by square root of 1 plus F by Fh whole square. In the third case, at frequencies f much greater than fl and fh, the terms f by fl whole square and f by fh whole square in the denominator will be very large in comparison to 1. Therefore, modulus of V0 by Vn is equal to AFT into f by fl divided by square root of f by fl whole square into f by fh whole square. This equals AFT into fh by f. That is, gain is inversely proportional to frequency. As frequency f increases, gain decreases, which is shown in the figure. Let us next discuss the narrow bandpass filter in detail. The circuit diagram of a narrow bandpass filter is shown in the figure. It may be noted that the filter uses only one op-amp in contrast to wide bandpass filter which uses two op-amps. Also, it has certain distinct features in comparison to all other filters. First, the filter has two feedback paths because of which a narrow bandpass filter is also called as multiple feedback filter. It uses op-amp in the inverting mode. The expression for the voltage gain can be obtained by applying the Kirchhoff's current law at node V2. At node V2, I1 plus I2 plus I3 equals I4, or equivalently, Vn minus V2 divided by R1 plus S into C2 into V0 minus V2 minus V2 by R2 equals V2 into S into C1. On rearranging the terms, we get V2 into, within the brackets, 1 by R1 plus 1 by R2 plus SC2 plus SC1 brackets close minus SC2 V0 equals Vn divided by R1. Similarly, on applying Kirchhoff's current law at node V1, we have I4 is equal to IF, since node V1 is at virtual ground. Therefore, S times C1 into V2 is equal to minus V0 divided by R3, or V2 is equal to minus V0 divided by SC1 R3. Substituting for V2 from equation 14 in equation 13, we get minus of V0 divided by S into R3C1 into, within the brackets, 1 by R1 plus 1 by R2 plus SC2 plus SC1 into brackets plus SC1 brackets close minus SC2 V0 is equal to Vn divided by R, or the ratio V0 by Vn can be obtained to be equal to minus SC1 by R1 divided by 1 by R3 into, within the brackets, 1 by R1 plus 1 by R2 plus SC2 plus SC1 brackets close plus SC2 into SC1. Dividing the numerator and denominator by C1 C2, we get V0 by Vn equals minus S divided by R1 C2 divided by 1 by R3 C1 C2 into, within the brackets, 1 by R1 plus 1 by R2 brackets close plus S into, within the brackets, C2 plus C1 divided by R3 C2 C1 brackets close plus S square. This can be simplified to obtain V0 by Vn equal to minus AF into omega naught S by Q divided by omega naught square plus S omega naught by Q plus S square, where S is equal to J omega and omega is the input frequency. Omega naught equals 2 pi Fc is the center frequency. Capital Q is the quality factor and is the gain at center frequency Fc. And AF is the gain at center frequency Fc. Equating the corresponding coefficients, we get omega naught square is equal to 1 by R3 into C1 C2 into, within the brackets, 1 by R1 plus 1 by R2. The ratio of omega naught to Q is equal to C2 plus C1 divided by R3 into C2 C1, and AF into omega naught divided by Q is equal to 1 by R1 into C2. In order to simplify the design calculations, let C1 is equal to C2 equals C. So, the above equation reduces to omega naught square equals 1 by R3 C square into, within the brackets, 1 by R1 plus 1 by R2. Omega naught by Q equals 2 divided by R3 into C, and AF omega naught by Q equals 1 by R1C. Resistors R1, R2 and R3 can be obtained in terms of narrow bandpass filters parameters, that is Q, Fc, or equivalently omega naught, C and AF. So R1 is equal to Q divided by AF into omega naught C. This equals Q divided by 2 pi Fc AFC. R2 is equal to Q divided by 2 pi Fc into, within the brackets, 2Q square minus AF. R3 equals 2Q divided by omega naught C, which equals Q divided by pi Fc into C. The gain at Fc, which is AF, is equal to R3 divided by 2 times R1. The maximum value of gain is limited by the quality factor. Gain AF of narrow bandpass filter must satisfy the condition AF is less than 2Q square, since R2 cannot be negative. Therefore, in order to analyze the variation of gain as a function of frequency, we consider the expression for gain, that is equation 15, and apply some special cases. First is the case when omega tends to 0. As omega tends to 0, terms in the denominator S omega naught by Q plus S square can be considered to be very small in comparison to omega naught square, and thus they can be ignored. So V naught by Vn tends to 0 as omega tends to 0. Second case, when omega tends to infinity, as omega tends to infinity, omega naught square in the denominator will be very small in comparison to S omega naught by Q plus S square, and thus can be ignored. So V naught by Vn equals minus AF omega naught by Q divided by omega naught by Q plus S, which tends to 0 when omega tends to infinity. Third case is when omega is equal to omega naught. In that case, in here, V naught by Vn equals minus AF into omega naught into j omega naught by Q divided by omega naught square plus S omega naught by Q plus j omega naught whole square. This equals AF, which is the mid-band gain. The figure shows the variation of gain of narrow bandpass filter as a function of frequency which is described. It may be noted that the gain is maximum at a frequency omega equals omega naught and falls on either sides. We will next study the band reject filter. The operation of a band reject filter is opposite to that of a bandpass filter. It is a frequency selective circuit which attenuates a particular band of frequencies while passing through it and allows the rest. Similar to the bandpass filter, band reject filters are also classified as first, wide band reject and 2, narrow band reject filter. Wide band reject filter has a small value of Q, that is Q less than 10, whereas narrow band reject filter has a large value of Q, that is Q greater than 10 due to small bandwidth. Let us next take up the wide band reject filter. A wide band reject filter consists of a low pass filter, a high pass filter and a summing amplifier. The circuit of band reject filter along with its frequency response is shown. The band reject filter response may be viewed as the sum of output of low pass filter and a high pass filter. In order to realize the band reject filter response, it is necessary that low cutoff frequency FL of the high pass filter is greater than the high cutoff frequency FH of the low pass filter. Also, the gain in the pass bands of low pass and high pass sections must be equal. The bandwidth of filter is equal to FH minus FL. We next discuss the narrow band reject filter. The narrow band reject filter is commonly known as a notch filter and is used for the rejection of a single frequency such as 60 Hz power line frequency hum. The circuit of a notch filter is a T network, which is a passive filter composed of two T-shaped networks connected in parallel. One of the T networks is made up of two resistors and one capacitor, that is R, and 2C, whereas the other T network is made up of one resistor and two capacitors, that is C, and R by 2. The upper T network works as a low pass filter and the lower T network works as a high pass filter. A twin T network, as explained, used in a notch filter is shown in the figure. The analysis of the notch filter can be carried out by converting the two T networks into the equivalent pi networks. The pi equivalent circuit is drawn in the figure where ZA equals 2R into within the brackets 1 plus j omega RC. ZA prime equals 2 into within the brackets 1 by j omega C minus 1 by omega square C square R brackets close. ZB equals ZC equals ZB prime equals ZC prime equals R plus 1 divided by j omega C. Slide number 18. The circuit shown in the previous figure can be reduced to that shown here, where ZA double prime is equal to 2R into, within the brackets, 1 plus j omega CR divided by 1 minus omega square C square R square, brackets close. ZB double prime equals ZC double prime equals 1 by 2 into, within the brackets, R plus 1 by j omega C. The complex transfer function is given by V naught of omega divided by Vn of omega equals Zc double prime divided by Za double prime plus Zc double prime, which equals 1 minus omega square C square R square divided by 1 plus 4 into j omega Rc minus omega square C square R square. The absolute value of the complex transfer function is given by modulus of V naught of omega divided by Vn of omega equals modulus of Zc double prime divided by Za double prime plus Zc double prime. This equals 1 minus omega square C square R square divided by square root of 1 minus omega square C square R square whole square plus 4 omega RC whole square. Or equivalently, it may be simplified to obtain the modulus of V naught of omega by Vn of omega to be equal to 1 minus omega by omega n whole square divided by square of 1 minus omega by omega n square plus square of 4 omega by omega n. Here omega n equals 1 by Rc and corresponds to the notch frequency. The above equation shows that for fixed values of R and C, omega n is fixed and the output voltage depends solely on the frequency of input signal. When omega equals 0, modulus of V naught of omega by Vn of omega equals 1. The filter possesses a flat band gain of 1 at low frequencies. When the input frequency omega equals omega n, then the modulus of V naught of omega by Vn of omega equals 0. That is, output voltage is 0 at the notch frequency. In the case when omega tends to infinity, modulus of V naught of omega by Vn of omega equals 1. The filter in that case possesses a flat band gain of 1 at low frequencies. A passive notch filter, which was shown in the figure 9, suffers from various drawbacks. Firstly, the gain of the filter at frequencies less than the notch frequency is not same as that for frequencies greater than the notch frequency. This is because of the higher voltage drop across the two resistors in the low pass filter section in comparison to that across the capacitors in the high pass section, leading to lower gain at frequencies f less than fh. Secondly, the notch filter possesses relatively low figure of merit Q, which corresponds to a large bandwidth. Such large bandwidth is not desirable for various applications. The figure of merit Q can be increased by integrating the passive T network with the voltage follower, resulting in active notch filter, which is shown in the figure. Let us discuss about the frequency response of active notch filter. The frequency response of active notch filter, as shown, reveals that the circuit exhibits a flat response where the voltage gain equal to 1 over the entire frequency range except a particular frequency called notch frequency Fn. It is the frequency at which maximum attenuation occurs, where Fn is equal to 1 divided by 2 pi Rc. Thus, the name notch filter is derived by the ability of the circuit to notch out or block frequencies near Fn. Notch filters are highly useful in situations where it is necessary to attenuate a single frequency, which is responsible for generating electrical noise such as that generated from inductive loads, motors, etc. Notch filters find increasing applications in communication and biomedical instrumentation for eliminating unwanted frequencies. In the last, we will discuss about the all-pass filter. An all-pass filter, in accordance to its name, allows all frequency components of the signal to pass through it without attenuation but introduces predictable phase shifts for different frequencies of input. These filters are widely used as phase compensators when signals are transmitted over transmission lines such as telephone wires, leading to phase change. All-pass filters are therefore also commonly known as delay equalizers or phase correctors. The circuit of an all-pass filter is shown in the figure. RF is said to be equal to R1 in the circuit. The output voltage V0 of the filter can be obtained by using the superposition theorem as V0 equals minus Vn plus 2 into within the brackets minus jXc by R minus jXc brackets close into Vn. Substituting Xc equals 1 by 2 pi Fc, where F is the frequency of input signal in Hertz, and simplifying, we get V0 to be equal to Vn into within the brackets minus 1 plus 2 divided by 1 plus j into 2 pi f RC, or V0 by Vn equals 1 minus j into 2 pi f RC divided by 1 plus j into 2 pi f RC. The above equation shows that the amplitude of V0 by Vn is unity or constant for all frequencies, which implies that the magnitude of V0 equals magnitude of Vn for the entire range of frequency. The phase angle phi between the input and output voltage is a function of frequency and is given by phi equals minus 2 into tan inverse 2 pi f RC divided by 1. If the parameters R and C are fixed for a filter, then the phase angle phi can be determined using the above equation. The expression for phase also reveals that as the frequency of input signal is varied from 0 to infinity, the phase angle phi changes from 0 to minus 180 degree. The figure shows phase shift between input and output voltages for an all-pass filter where V0 lags Vn by 90 degree. If the position of R and C are interchanged in the circuit for all-pass filter, then the phase shift between input and output signal becomes positive. That is, output leads the input signal by angle phi. So students, let us now summarize what we have learned in this module. In this module, higher order filters such as third order and fourth order were discussed. The types of bandpass filters, that is, wide bandpass and narrow bandpass filters, were studied. The expression for gain for narrow bandpass filter is derived and the frequency response was obtained. Band reject filters was studied as wide band reject and notch filter, and the frequency response was discussed in detail. An all pass filter was studied. Thank you students for your attention.